Oh yeah, the tour. So all right. So who's going to do the tour? Anybody? Oh, 3, 4. All right. So we can do it.
And one more, who's in here today?
All right. Okay. So if you put down GCWW into Google Maps, and there's one that's like Kellogg Avenue, like cereal. That's the place. Then if you go there, yeah, I need to give Jeff your names. So he's pretty eager to do it. He said he'd do it for one person. I was like, oh, it might just be like 5. He said, doesn't matter how many. So it's kind of a desperate place, I guess. But yeah, when you pull in, so like when you pull in up above, there's a golf course, and there's ponds on the golf course, and those are the holding ponds for the Cincinnati's water. Like they pump from the Kentucky side of the Ohio River. You'll see if you come on 275, there's 2 ways to get there. You can go on 275. If you look down off the bridge in 275, there's like the tower. That's the intake for Cincinnati's water. And then it goes under the river and then up onto that golf course, into the ponds on the golf course. And then it feeds by gravity down into they have like fan beds or something that filter the water outside with big turning arm things. So I don't know. And then it goes from there. There's like a settling pond area that's like 3 or 4 football fields indoors, Then it goes from there into a carbon filtration, which is pretty cool to see. Then they have a big activated carbon rejuvenation plant there, and I don't know, it's pretty neat. Then there's like a UV treatment, so it's pretty neat. It's big, it's a big facility. Like all the water, like it's the cleanest water in the country, I think.
Cincinnati.
Yeah, because they had a bunch of problems.
Oh,
Yeah, so they had to do. So it's the only place where they do carbon filtration.
Oh, that's crazy.
Yeah, and I think it's one of the only places that UV treats the water. That was so each of the things and steps in that sequence were due to some event that happened. Yeah. So and the things they don't know is like PFAS and drugs, like I think they don't have a way to remove some drugs. Because when you take drugs, like you pee it out. And then also people dump the drugs down the drain, like when they're done with them. So that all gets into the river.
So you just get like microdosing.
Yeah, you're microdosing all kinds of weird drugs. Yeah.
That's crazy.
Yeah. So could explain a lot of like what's happening to people, but yeah. Anyway, so that's good. All right. So I'll tell them, so yeah, send me your name so I can give them the name list. And then if people aren't on the name list, they can still come, I think. Like you can take it there, but basically it'd be better to have them so you can kind of prepare. And then I don't know, it's pretty good. Like if we can get a group to go, I think it's pretty good to do. Oh no, I clicked update now. Oh, I think that was a mistake, but actually it didn't do anything. So I have like 2 sets of slides, and I don't know, I'm not sure why I mean, it's the same thing, I think, but I went through both of them. They seem to be a little different. Anyway, so okay. So basically, I started talking about this. This set of slides is shorter. Actually, it's 208 slides, so it isn't that short. The other one has more. I'm not sure what the difference is between them, but basically the idea is like this one's called ammonia, like ammonia something, and the other one is just isn't called that. But basically the idea is like hydrogen economy is a concept. So again, like this is hydrogen economy in the US isn't exactly here yet, but in certain countries like Saudi Arabia, Germany, Australia, Japan, like it's the main thing that they're doing. Like everybody is just doing this. Now, so it's kind of like the US is really going towards electric batteries and things, and all those other countries are kind of going to hydrogen. But in the end, like the petrochemical is going to be kind of hydrogen driven. So that seems to be like there isn't really going to be a choice. We'll be going hydrogen at some point, right? So anyway, they talk about different varieties of hydrogen, like green. So you use photovoltaics or wind or hydro, and you do electrolysis and make hydrogen. And then blue is where you do methane reforming. So most of the hydrogen we have now, like you buy a tank of hydrogen, it came from methane. So natural gas, and then it's reformed to produce hydrogen. And then if it's blue hydrogen, in that process, so the carbon dioxide is trapped. Let's see, do I have an equation for that? Yeah, steam reforming of methane, right? So you take methane, natural gas with water, with a catalyst at high temperature, and you can form hydrogen and carbon monoxide. So that's syngas. So carbon monoxide burns. You can burn it as a fuel, right? So anyway, and then if you that's for what do they call black hydrogen or something? Brown or gray hydrogen. And then the blue hydrogen is this process, like you take methane, water, heat, catalyst, and then you can, because it's producing carbon dioxide, hydrogen, carbon dioxide is polar. So basically you can separate out the carbon dioxide by pressure swing absorption. So you have like a zeolite, porous ceramic, and then the carbon dioxide precipitates out first. So you pressurize it and the carbon dioxide separates. You can take out the hydrogen and you depressurize it and you get the CO2. It swings because it goes through cycles of pressurized, depressurized. You have two of those usually. One's pressurized, one's depressurized. It's like a breathing thing. Same way to make oxygen. To make like in a hospital when they have an oxygen machine. It's a pressure swing absorption. So basically, anyway, so you can make kind of cleanish if you capture all the CO2 and then and the carbon monoxide, and then you convert the carbon monoxide to CO2 by oxidizing it, basically burning it, then you can kind of capture all the CO2 that's produced and do something with it, like bury it underground. So nobody does that. Like that doesn't exactly exist, right? So most of the hydrogen we have now is produced like that. And then that hydrogen you can use to make ammonia, right? Let's see. That's where this set of slides should be better. So you can use that hydrogen. All right, so you can run this reaction backwards too. Like you can take hydrogen, CO2, and run this reaction forward or backwards. That's the shift gas or gas shift reaction, right? So you can water gas shift reaction. So you can have that. You can have a reverse WGSR. You can have a forward, depending on what temperature you run it at. So you can take, if you can produce hydrogen, then you can make carbon monoxide, right? So if you have carbon monoxide and hydrogen, then you can use Fischer-Tropsch reaction to make hydrocarbons. So you can take hydrogen and carbon monoxide, depending on the number of moles of carbon monoxide you put in, you get different length carbon chains. You can make wax, you can make ethane, ethylene, you can make waxes, and you can make like just long, like polyethylene basically from it, right? Just by cooking it. So you can make, from that root, you can make kind of like any petrochemical, like by combining up hydrocarbons, just by cooking hydrogen and carbon monoxide together, right? So that's kind of the scheme. So once you can make the hydrocarbons, you can make anything, right? So key to it is getting hydrogen somehow, right? By splitting water somehow, right? So you can do all these reactions if you can split water. So basically, if you put in a platinum anode, then you can electrolyze water, like with enough electricity. Right. So it's possible to split water with just electrochemical cell. Right. So if it's salt water, it's harder. You can do it with, it has to be pure water. So somehow you can purify the water by putting it through membrane osmosis, reverse osmosis, and then do this electrolysis to make hydrogen. Right. So if you have a source of electricity, then you just make hydrogen. So that's the idea of like basically use PV, wind, hydro in some odd location where you can't use the electricity there and use it to make hydrogen. But the problem with hydrogen is the transport. Right? So let's see. That's what a pressure swing absorption unit looks like. Like it's two pressurizing, depressurizing units next to each other. Right. So right now ammonia is also made by methane from, right. So all the hydrogen, most of the hydrogen we have now is made by this kind of methane water reaction, steam reforming methane. And most of the let's see, the ammonia reactions in here too somewhere. It might be that the other one's better, or the Haber process, right? So basically, you start with methane, put in air, it's got oxygen and nitrogen in it, and then feed that into a reactor. You make hydrogen from the methane. So this is water shift gas reaction. So you have water and hydrogen. Water and methane makes hydrogen and CO2. And then you take out the CO2. Could be a pressure swing absorption to do that. Use a compressor, you have nitrogen and hydrogen, and then feed that into a iron catalyst at high temperature and pressure. So 300 atmospheres, 30 megapascal. So the Haber process reactions going on here, and that'll make ammonia. And then ammonia you can turn into uric acid or something later on. Like the fertilizer would be uric acid, but it's a direct cycle to get from ammonia to uric acid. So ammonia itself, so basically in this step of the process, so you make ammonia, which is like propane, like one megapascal, so 10 atmospheres, it becomes liquid. Hydrogen, you need to have this huge pressure, like 100 atmospheres. So you need thick steel barrels to have a hydrogen, liquid hydrogen, right? And then ammonia, you can just have a normal like propane tank. So basically, we already have all the technology to work with liquid ammonia, pure liquid ammonia, right? And liquid ammonia, you can burn it and it burns into like water and nitrogen. So it's perfectly clean fuel to use, right? So ammonia is kind of one of the keys to this whole hydrogen economy. For one thing, you can transport it in a propane tanker. So there's already ships built that can take ammonia you can ship it around the world. So you can make it. So the north part of Australia is just all desert. Not many people live there. There's a lot of ports. And they're setting up like solar farms there, huge solar farms that are just being used to, there's nobody to use the electricity. They're just making hydrogen. And then they're converting the hydrogen using the Haber process to make ammonia, and they're putting ammonia on ships and shipping it to Japan, where there's a lot of people, like it's huge population density. So And then in Japan, they're taking the ammonia and they're converting it back to hydrogen. Right. And they're taking the hydrogen and they have like hydrogen cars in Japan. So like I think a quarter of their cars are hydrogen cars. So they have like everywhere you go, there's hydrogen fuel stations. So basically hydrogen's their choice versus batteries. Because the fueling is the same as fueling from a gas station. It takes like a couple minutes to fill up the car with hydrogen. I mean, there's some problems with it, but basically it's probably safer than gasoline, you know, in the long run. So it doesn't stick to your skin when it burns. It's lighter than air, so all the flames like lift off away. It's basically if there's an accident and there's a hydrogen leak, the hydrogen goes away. The gasoline doesn't. Gasoline sticks to people and burns, right? So gasoline's a much more dangerous fuel to use. It's also got a lot more BTUs in it than hydrogen. So somewhere in here, let's see, somewhere in here is a comparison of hydrogen. I thought it was at the beginning, maybe. Comparison of fuels, right? So ammonia, hydrogen, gasoline, liquid propane, natural gas, and methanol, right? So the bottom line is like dollars per gigajoule, right? And this is ammonia that's made by the Haber process from methane. So it's like cheaper, it's the cheapest fuel that you can find. It's cheaper than bunker fuel, even the commercial ammonia that's made right now. It's like probably we could convert to ammonia fuel for some applications like ships, like right now. We wouldn't have to wait for a green economy or hydrogen economy. And then gasoline's at 30 cents and hydrogen's a little bit more expensive, right? And then some other options like propane, methane are like kind of in the same range as gasoline. Methanol from corn is a lot more expensive, $1 per gigajoule. Then there's also the issue. So ammonia wins money wise, even just ammonia that we have now. And then this issue of like how to store it, right? So gasoline wins on the how to store it thing because it's got a lot of energy and it's liquid at room temperature with no pressurization, 1 atmosphere pressure, right? So, and then so even then, like ammonia and hydrogen are kind of competitive, even in terms of volume. Once you liquefy ammonia, right? I mean, there's some issues like when it burns. So what people are thinking about, at least initially, is to mix ammonia with like gasoline or propane or something to get a better flame because it doesn't burn as well. Like it doesn't have as good of a burning process. Like there's a picture of it burning here somewhere. I don't see it here. But anyway, on the other side of slide, picture of an ammonia flame. And it's not as nice as an ammonia methane mixture thing. Let me see. Where's that table again? Here. So sorry, that's yeah.
Unless I'm reading this wrong, isn't that the cost dollar per meters cubed? So you want a lower number?
Yeah, but a meter, right? You'd want a lower number. That's true. Yeah. But well, that's good point. But basically, a meter cube of gasoline has a lot more firepower. I guess energy density, right? 34 per meter cube. Yeah, you're right. That's a worse number. The best number would be like hydrogen. But 1 meter cube of hydrogen only has 3.6 gigajoules. So it's 10 times more. So it'd be like 1,250. Anyway, whatever. Yeah, you're right. That's right. Yeah. I mean, gasoline has a lot of advantages, you know. It's basically, but if you figure out like how much oil it takes to make a gallon of gasoline, like from in other words, you start with crude oil and then you have to refine it. All right, you have to dig it out of the ground first. And it's coming from some deep well at this point. So the finding the oil to begin with is a huge process, and transporting it to the refinery is a huge process, and then refining it's really big process. So just the refining part of it, I think it's a 4-to-1, so like 3 or 4-to-1. Like you're burning off 2 or 3 times the gasoline to make a gallon of gasoline, right? So the refining process is a real dead end, and all the mining it and shipping it is a big problem too. Then transporting it out, so like transporting the gas is easier than transporting a liquid because you can pipe the gas, I guess, like natural gas pipelines and stuff, you know. So anyway, so some like it's a lot of in the danger of gasoline because it's basically it's a really dangerous thing to carry around in pretty thin gas tanks, right? They can burst open easily. There's a lot of disadvantages to gasoline, and it's a carcinogen, right? So the fumes, if it was discovered today, and you went to, and they were going to say like today, and you're going to go invent this fuel, and then you'd have to fill up your car, you would definitely need to wear a respirator or something. You know, they wouldn't let you breathe, or there would be a huge fume hood at the gas station to suck off the fumes. So if you think about like handling benzene, so it's like handling benzene, right? If you handle benzene in a lab today, like you have to wear all kinds of gloves, and you would never do it outside of the hood. The only reason was it was discovered like such a long time ago that it's conventional and people aren't afraid of getting cancer from it. It's actually pretty nasty. Anyway, if you look at kind of discovery of new things and you thought about gasoline as an option, it would probably not be the first option to pick for fuels. Wait, what else do we got here? So right, so there's dirty methane that comes from the ground, some natural gas, and there's also you can make methane, so by several methods, right? So what's this thing? This is the Fischer-Tropsch reaction, right? So you can take hydrogen if you have carbon monoxide. You can make any kind of, you can make fuel, so you can make a liquid fuel, or you can make plastics, right? Just through a high temperature reaction, right? And water is a byproduct. Oops. And then and this is how they take ammonia and turn it into hydrogen, is cracking. So you have take some energy, you make hydrogen from ammonia, right? So over some catalyst, like a metal catalyst. Right, so you can get like Malbing 2 is going to come on Tuesday, like a week from Tuesday, to talk about biofuel, right? So that's so I mean the simplest thing is just these kind of scrap reactors. I mean, this is in India, so basically food scraps in a barrel, let it bacteria react with it, makes methane, and you can just tap it and like burn it, right? So this is in the US. People have these methane storage things from basically food waste. So you fill a bucket with your food waste, dump it into it, and then you can have like a balloon or something that holds the methane gas that comes out, right? And then in Africa, this is with manure from cows, and they fill the manure into this trough thing. Then these are just plastic bags full of methane, and they can kind of sell the methane that way. This is in Kenya, I think, but there's video on that. But basically, so it's possible to make methane not from a petrochemical aspect, right? That's an option that could feed right into the this whole kind of hydrogen economy thing. So you use the shift gas reaction to make hydrogen, then hydrogen to make ammonia, and then basically you can kind of feed into that from a variety of sources, not just from solar energy. And then algae can make hydrogen too. So, but the algae production of hydrogen is like a failed. There were actually companies that were doing this in California with government subsidy, and they all failed basically. So even though algae production seemed like a pretty good idea, it never really worked out, right? So basically, the algae thing remains like kind of a pipe dream. You can see people built giant algae reactors of various forms to try to make hydrogen to feed it into this cycle. And it's possible to do, but it hasn't like reached fruition, I'll put it that way. It's been around for 20 years probably. So that leaves you with how to make hydrogen, right? So one thing like titania is like silicon, is a semiconductor. When light hits it, it makes electrons, like those will oxidize. So you can oxidize water, or you can reduce water and make oxygen, and you can oxidize or the OH and make hydrogen basically from a titania surface, right? And then so the original process I mentioned before was this Honda thing, like 72. So this is basically he's just shining sunlight in on a titania surface. He's got a platinum electrode and he's got titania on the cathode, and he's making oxygen on this side, and he's making hydrogen on the platinum side. Basically, you can just have an electrochemical cell driven by solar energy and make hydrogen. The problem is that the absorption of titania is in the UV and it only takes like 5% of the total solar spectrum. So it doesn't, it's not an efficient way to do it, right? So in fact, that kind of semiconductor approach to making hydrogen, I guess was seen as not really functional, even though groups are doing it in Australia. Like there's research groups that are looking at that. So anyway, the main process that people are looking at is a solar concentrator thing, where you can take a metal. So you take water, and then if you have a metal in the ground state, the water will rust it. So you make an oxide, right? And then what's left over is hydrogen. So if you rust iron, you're making hydrogen already, right? So anytime you have rust, you made hydrogen. So basically, you can turn that into a chemical cycle, because if you take rust and you put it into a solar reactor and heat it up to 2000 degrees, it releases the oxygen, and then you can feed it back in as ground state metal and do that process again. So it's possible to have this cyclic thing where you're using sun energy to reduce the metal oxide to get ground state metal, and then you're splitting the water with the metal to get hydrogen. And you carry the oxygen over and reduce it, get oxygen, and just kind of go through that cycle. So there's various schemes that people have dreamed up for doing this. So this turns out to be much more efficient than trying to do electrolysis with titanium and sunlight. And so, but there's problems. So usually metal oxides are solid, like they're crystal. So basically, and because you want to have this reaction, so it's a gas phase reaction in both cases. So you're going to have a surface area to the metal in order to make this happen. It means you have to have like nanoparticle oxides going through this. And then you're going through a conversion of nano-sized metal oxide to ground state metal nanoparticles. So this is all done as an aerosol. Like this would be like an aerosol stream running through this. And that's one option. Another option is you can take that metal oxide, and if it's the right kind, you can make fibers with it. So you can make really small fibers, and then the fibers can just kind of circulate through this cycle. Right, so you don't need to have particle aerosol. You could have a solid fiber going through this process, or you could make a porous solid wheel out of the oxide and make the wheel run through a circle, like rotate it. That's called the Sandia reactor. Right, so there's various ways to do that. Right, so anyway, people have tried all those, and there's another way that you can do it. And they've tried there's a whole bunch of different oxides that can be done. They've also used sulfuric acid to do this, coupled with a so let's see what I have here. This is one option. We use cuprous chloride. So this is a liquid state reaction. So you have cuprous chloride. So most of these liquid state reactions it's really electrical electrolysis, but like the oxidation step is done. The oxidation step is done with the metal, right? So you oxidize the metal and then the electrolysis the hydrogen off. It's a two-step reaction. Electrolysis takes about half the energy that it would take if you had to also run the oxidation step. So you're cutting the energy requirement for it, but you aren't getting away from having electrolysis set up to do this thing. Right. So the advantage is you don't have particles that, as it goes through the cycle, the aerosols of particles grow and grow and grow, and also the fibers get thicker and thicker and thicker until they aren't of any use anymore. So the one case you have to throw away a kind of catalyst that you're using to make hydrogen. The other case, in this case, you have liquid solutions that regenerate themselves. It's better, in that sense. So you don't have the cost of like reproducing the nanoscale particles that you're using in the reaction. So some kind of liquid state process is probably a better option for this. That's just showing this chloride process for this. So again, they're like feeding in electricity to do electrolysis, but the reduction stage of the thing is being driven by the or the oxidation stage is being driven by the water combining with the metal. This is an iron oxide process. So the advantage of iron oxide is that, I mean, it's non-toxic. It's like everywhere. So there's a scheme. There's the aerosol particles flying through this thing. This is a kind of one of these aerosol reactors for this. And you can see it's a lot of piping. So it's kind of a so one side. The idea is one side does oxidation, the other side does reduction in this scheme, like a dual cylinder operation, and the streams feed the metal oxide aerosol through this, right? And somehow you can separate the hydrogen and oxygen streams in that process. Let's see. This is another aerosol reactor. This is a Swiss reactor. So basically, there's like a tornado of aerosol particles flying through it. There's a solar collector, right? And then this is set up. This is a case of this is ceria felt. So these are like fairly small ceria. It's going to go through an oxidation reduction reaction. And this thing is usually on some kind of a mobile platform, right? So it rotates through the oxidation reduction. That's just showing the results, like where it produces oxygen and the same fiber produces hydrogen. Temperature dependence. This is over multiple, like when you get to 10 cycles, how that thing works. So this Swiss group thought that ETH is like the Zurich MIT thing. So they came up with it. They needed 20% for commercial use by comparing it to PV panels. And then they're getting something lower than that, basically. 1 cycle and 10 cycles through this. This is zinc oxide cycle is kind of similar. So there's a whole slew of these metal oxide. That's a different aerosol reactor using zinc oxide. And also showing like oxygen release and hydrogen production. Right, these are the places where they have these test beds. So this isn't commercialized yet. So it's basically run on these kind of test beds. This is Ordello, France. This is just a bunch of mirrors focused down on a reactor sitting here. So it's not really a conventional way. I think they built it because they had a building and they attached it to the side of it somehow, But basically, you would have a solar field. You wouldn't do it that way. Like you'd have a solar field with mirrors that tilted so that you could improve on that. You could get the light set. This is a Sandia solar test reactor. So they have this special so they make a ring of the metal oxide that rotates through oxidation reduction reaction. So they're kind of spinning it through. So the advantage is they don't have a heat up and cool down process on it. And they can produce, and they're reducing carbon dioxide to make carbon monoxide. So there's two ways to do this. You could make hydrogen, or you can make carbon monoxide. If you can make carbon monoxide, you can use it to make CO2 and H2 from water. Like if you combine carbon monoxide with water, you can make hydrogen from it. Or you can just burn carbon monoxide. Or you can mix it with H2 to make syngas, which is another fuel. So, or you can use it carbon monoxide plus hydrogen, the Fischer-Tropsch, and you can make hydrocarbons with it. So some advantages, and also, so they're saying they're going to consume. So you could have a carbon fuel plant, like a coal fuel plant, take the CO2 that's coming off and feed it into a solar reactor like this to make carbon monoxide, and then use that carbon monoxide in the other reactions. So there's a lot of options here. That's a picture of this Sandia ceramic reactor core to the thing. Let's see. So this is another Sandia developed process, this hybrid sulfur cycle. So this is it's a liquid state cycle, sulfuric acid. And then if you heat up sulfuric acid to 800C with a solar concentrator, it splits into sulfur dioxide and water. And then the sulfur dioxide will combine with water to make hydrogen and then sulfuric acid. Right. So in order to get this step to go water, sulfur dioxide, you need to do electrolysis. You have to put in an electrochemical cell. Right. So this is, it's all liquid, so there's no nanoparticle or fiber growth problem with this. But basically, you'd still need to do electrolysis on it. So it's kind of missing a step. So they came up with this idea that you could use hydrogen iodide in this process. So if you take hydrogen iodide, heat it up to 450C, it'll produce hydrogen iodide ions that you can feed into a reactor at 120 with water, and then that will remove the need for, it'll make hydrogen iodide from water, and it'll make OH minus that can combine with the SO2 molecule from the water to make H2SO4. Right, so they don't have any electrolysis and they're producing hydrogen, and it's all liquid state. The whole thing's being done in water. Right, so it's just a bunch of pipes. It's got 3 ovens, all of which can be driven with solar power, and you're just taking water and making, and nothing is consumed in this. Right, so just taking water and making hydrogen and oxygen directly from sunlight. You have to have 3 different temperature ovens in this thing. Right, so that's kind of the simplest scheme. Like that's the nicest thing. You don't have any nanoparticles. There's no ceramics, just sulfuric acid, hydrogen iodide. That's it. And so, sorry, that's kind of the I guess the optimum of these processes to make hydrogen. It's all liquids. I don't know. So that process is kind of seen as like the premier of these things. And they can get, but people still propose like more and more complicated setups to do this thing. Like, I mean, there's a lot of different processes to go at this, and like this is kind of a recent. I feel like this is like 2021, I think. I think this was in Nature or something, but it's kind of like just a really complicated process. I don't even know what all the components are. I mean, it produces hydrogen, it produces oxygen, and it uses water. But other than that, it's pretty complicated. It's magnesium and then sodium. I guess that's it, magnesium and sodium, but who knows exactly what's going on in this thing. So there's a series of reactions here that somehow produce hydrogen and oxygen, and it's an oxidation reduction reaction. let's see, someplace is a table of all of these reactions, like comparing. Yeah, okay. This is a comparison of all the possible or existing like processes, I guess, of different systems and trying to figure out like what's the best one to use. Right. So people have like categorized these and figured out like what's the best process to use to produce hydrogen from solar. Right? So that's kind of a list of the candidates for this thing. This is another solar reactor that's in the US in Colorado. And that's a, this is a power generation solar field. So the idea, like these are research fields, right? Solar concentrators, but the actual, this is a like a small scale power generation, California, right? Where it's a field of mirrors. They focus on that one spot to heat up molten salt, basically, then use a steam plant to make electricity. That's another research one in France. This is a research in Spain for that same kind of solar reactors. Germany has this DLR research reactor. And that's a commercial power generation, solar concentrator power generation. Same thing, that's in Nevada. Anyway, so that's kind of one picture of what's going on with this stuff. Not sure what's in the other. Anyway, I think that's pretty much what I wanted to talk about. Then the other thing is like, so you can make hydrogen and feed into the hydrogen economy, and then you can also just tag on solar to replace hydrocarbon fuels in the chemical industry, right? Rather than just trying to talk about solar as a standalone, it can be just an add-on, you know, to chemical processes to replace heating, like fuel-based heating. And so people have looked at that too, like, and in some cases it's been used. So this guy, so Weimar, I usually get him to talk, but he doesn't talk about this stuff. So he talks about what he's doing for research, which isn't this anymore. Like he did, Weimar's a guy from UC, like, and he's on the board of directors or something for chemical engineering. Like they have an industrial advisory board. So he's a pretty good guy. He's nice. And he got his BS here. Then he went to Colorado. He worked at Dow. And he went back to Colorado and was a professor there. But he did this ALD thing, which is atomic layer deposition, where they start with a particle and you deposit like oxides on the surface of it. So it could be used, I mean, some of it was used for the solar hydrogen generation process, but it's also used mostly for catalysts, like to produce one single, because the catalyst material, like say you're gonna use platinum, then you want to have like as thin a layer of platinum as you can because it's expensive, and the zirconia, so base of it is like free, it's like dirt. So you're coating dirt with gold, basically. So you want to use the least amount of gold you could use. So his atomic layer deposition, he can put down like one layer of gold, platinum, you know? So it's not wasting any material. So it's huge advantage for catalyst production, and also for this solar thing, it was of some use too. Like he made, I think he was making the Syria oxide catalyst that way. So anyway, so yeah, he was part of a team that did a review of, that actually made these tables of all the different, like this table and that table come from this paper that he wrote with these other people that aren't from the US. Like Steinfeld is from Switzerland. I guess these other people are from Switzerland too. I guess I'm not sure about these other two. Basically, he's a Swiss ETH guy. He's from Colorado. These others are somewhere else. But anyway, so I didn't bring Weimar in this year because they thought, I don't know, it's not in topic here at all. It's just to see the guy, and I don't know, he's kind of getting old too, so it's probably not worth it. He's not that young anymore. Listen in the picture here, but he's still like a really good guy to know. Like he's really good. If you're thinking of grad school or something, I mean, he's good. It's a good program in Colorado, and it's like a skiing place and stuff. So it's good to go out there. But anyway, yeah, so people have schemes like how to fit all that together, like into a whole economy. Um, anyway, so another thing is to just like use the solar heat to drive chemical reactors, and people have done that. This is also like PSI is like the main research lab in Switzerland, and then it's not far from Zurich. So, and Zurich's the top school probably in Europe, I guess. So they're kind of coupled together somewhat. And the PSI does a lot of this energy research type thing. So anyway, so they have some scheme to drive chemical reactors to make solar fuels from, it's kind of like using the heat to do chemical conversions. Energy use in the petrochemical industry, right? So megatons of oil equivalent. Yeah, so this is where they're using, it's kind of a plot of where the energy is being used, right? To make, in other words, to make gasoline. I guess piping it, and then production means like the wells, and then refining. See, all those things add up to like a huge chunk of what it, like the carbon footprint of gasoline is more than just burning gasoline. That's the idea, right? So, and all this is usually overlooked, right? But if you can, so if it's 2 times the gasoline gallon to burn to make the gasoline, but all you're using it for is to make heat, right? And you still want to use gasoline. Like you could cut your gasoline usage by 2/3 just by replacing the heat that you use in the refining by solar heat. And it could be like the solar concentrator to make molten salt, so you could drive the chemical reactions that way. Right, so it's possible you could replace all the heat in every chemical process with solar if you wanted to, without any change of the economy. Just don't buy gas anymore. You make your steam with the solar salt things, which is already being done. So anyway, it's possible to think about that, like the investment that it would take to swap it out like that for a big chemical plant. Now, usually a chemical plant, even a moderate sized one, has its own steam generating capacity, so which they use coal or something to do it. It's basically just swap that out for a solar field and a salt tanks or whatever. I mean, so it's possible to do that. So people, I didn't invent that, like that's been around. So, and it's been implemented in Texas. There's a couple places where they've done it, where it's, you can save money doing this. So, and it doesn't have to be 100% swap out. Basically, it's free energy. So there's a capital investment, but after that, the sunlight is free. So people have looked at like making carbon black, like burning to make carbon black. That's one of the areas where people have implemented like solar to do it. I mean, mostly that's not being done, but there's some cases of case studies kind of where people have done it in an industrial setting. But yeah, so anyway, this is just looking at the breakdown of the different kind of processes that use a lot of energy that could be swapped out with solar, some kind of solar concentrated thing. Anyway, so yeah, the drilling. So people have studied also just like the drilling of oil and like how you can swap out hydrocarbon fuel driven drilling with something like solar powered or electrified drilling, right? So it turns out there's a lot of opportunity. Like that's the bottom line. The petrochemical industry, even if you don't want to replace oil, like there's so much opportunity of wasted fuel, because the attitude is always like, well, we're making oil, it doesn't matter if we burn oil. Like that's just going to make more profit for us. It's a good thing to burn oil, right? So basically, if you can change that attitude slightly, you can still burn oil, but just swap out the things that you don't need to burn oil to do. I mean, it's basically going to be like more than half of the energy. So this simple swap outs that could just be done. Like in the case in Texas, where like I think a quarter of their power is wind power now. So it's like I mean, it's right there. Right, so basically, if you swapped out electric pumps versus diesel pumps to pump the fuel out of the ground, right? That it sounds like it's an insignificant thing, but it's like that's the production thing here. It isn't insignificant. It's like a pretty big chunk of energy being used just to do that. So anyway, I'm not sure why this is in here, but it just shows like the infrastructure in the US. And it's kind of impressive. You know, natural gas from Pennsylvania, New York, and Texas, and like you can get it like anywhere. I mean, the blue lines are like just the where you can tap into the line. Right? So it's just like if you look at countries like in Africa, they don't have that. You know, so that's why they're flaring off things. But anyway, so yeah, why don't we flip there? It's like because that's about. I have to kind of go through these slides some more. I thought you'd gone through these, but I guess I only came up to about here. So anyway, so yeah, Tuesday. So it looks like we'll go on the tour on Tuesday after class. Is that the idea? Go at 3?
Yeah.
20 minutes over there. All right. And then yeah, Tuesday I'll just kind of finish off this stuff. There's a couple other things I want to talk about wind power. I have some slides on that. And then next week, so then that's Thanksgiving. There's 2 more classes after that. So anyway, all right. So thanks. Yeah, it's good.
How did you-
You too.